Okay, we're ready to start up again with our panel session. Apologies from this end with the volume issues we were having before. I assume everybody can hear me okay now.
Yep.
Our next session is our panel session, which is to be run by Jan Vardaman. Jan is president and founder of TechSearch International, which has provided market research and technology trend analysis in semiconductor packaging since 1987. She's the author of numerous publications on emerging trends in semiconductor packaging and assembly. She's a senior member of IEEE EPS and is an IEEE EPS Distinguished Lecturer. She received the IMAPS Global Business Partnership Award in 2012, the Daniel Hughes Memorial Award in 2018, and the Sid Stein International Award in 2019. She's an IMAPS Fellow and a member of MEPTEC, SMTA, and SEMI. Before founding TechSearch, she served on the corporate staff of Microelectronic and Computer Corporation, MCC, which was down in Austin. Jan?
Hi, folks. Thanks for joining us. We have a really distinguished group of panel members. We've got Raja, who's joining us here from Austin, where I am. He's a senior fellow and advanced packaging leader at AMD. You've seen some of his handiwork announced recently. Tanay, who you just had introduced, who gave a very nice presentation from Intel. And then Ming Zhang is joining us from California. He's a distinguished architect at Synopsys. And then Tom Gregorich is joining us also from California. He's business development at Zeiss Process Control Solutions. So we prepared a couple of questions to start off our discussion, but we want there to be questions from the audience. So if there are questions, you know, like raise your hand and maybe Tanay can call on you and you can somehow type your question in or something, or yell your question in. So the first thing we wanted to talk a little bit about is what design issues does the industry face with the adoption of 3D IC? And do we have all the tools we need, or do these tools support like the co-design of timing and power domains and everything that we need? So Ming, why don't we start off with you?
All right, well, thanks for the honor. Thanks for everyone. Well, asking chip designers whether we have all the tools, that's like asking a kid whether you have all the candies you want, right? So my answer is that I think we have a pretty good set of foundational tools to do what needs to be done in terms of early architectural exploration, full design implementation, analysis, sign-off, and manufacturing enablement. But almost every single vector can be enhanced. And without dwelling too much, I would, for example, say that this whole topic of system co-design among different physics, right, timing and power and thermal and the interactions among chiplets, I think remains to be a challenge. So let me just pause here and hear from the rest of the panel.
So, I mean, you know, when Xilinx did their 2.5D, their silicon interposer, they had to actually go out and buy some software firms. So I'd kind of like to ask our Intel and AMD panel members, did you have to go buy any software companies, or what are you doing with your VA tools?
Okay, so let me take that. I'm from Intel. So no, we did not have to buy software companies, but definitely we are missing a system level view, meaning we have been struggling with system level analysis tools for anything new in our process. We own our process. So if the process research comes up with new memory, device, interconnect, packaging technology, attachment technology, material, we don't have any tools that can actually give you a system level impact. And how do we partition the systems to maximize the advantage of the new whatever is coming? Like for example, non-volatility. We always struggle to see what is the benefit of non-volatility in the entire system level puzzle. Although we can make non-volatile memories, we don't know how to use them how to analyze them at the system level before the fact. That has been our ask. System level tools.
Well, what about at AMD? Do you already have system level tools, or what do you do?
So it depends on what system level tools means, right? If you're looking at channel simulations, we typically do end-to-end simulations that accounts for like all the way from the silicon to the motherboard. And most companies do that, to my knowledge. I think the key question is, specifically for 3D adoption, are the tools mature enough in terms of understanding the different elements that I think Ming talked about, die-to-die communication, what are the right protocols? Are there the right timing issues, power dissipation, thermals? Clearly, there is no one tool that fits all so far. And especially since there are too many moving pieces just in terms of the technology definition itself, it's going to take a while for the tool set ecosystem to catch up to the technologies. Technology has always been leading the tool set ecosystem. And I'm sure with the right players in the mix, the tools ecosystem will catch up eventually. Right now, what we are doing is for our 3D chiplet architectures, we have some homespun tools that we are piecing together based on available industry capability, but that's not ideal. And I believe, I mean, Ming and I have talked about it offline on terms of what else can the ecosystem do better to move forward.
So do you guys think that the ecosystem, in order for this to be, some of these 3D IC designs to be more pervasive throughout the industry, are we going to have to wait till we have those tools available for these die-to-die designs, or you know, or people just going to cobble together something?
Nobody's going to wait for the tool ecosystem to be ready, right? If there is a product that has significant performance uplift, people will design. It's really up to the tool vendors to decide if they want to catch up or stay left behind.
I think it's a left foot, right foot, right? Product could lead tool development and could pull the tool forward. Once the tool is pulled forward, it would provide more capability to create better products. So let's not wait. Let's keep building. Let's keep flying the airplane while we build it.
Yeah, I mean, and that's true with any technology development, I think.
Yeah, exactly.
Nothing is going to wait for anything else. It'll keep moving on.
Yeah.
Okay. Well, another thing I wanted to talk about is along the same design areas where the thermal issue. Some of you guys remember, especially some of those old Intel mobile slides, when people were talking about 3D IC for the mobile space, they talked about hotspots heating up logic, you know, the logic from the logic heating up the DRAM. And that was when people were trying to stack the DRAM on top of the logic die instead of doing the package on package. And thermal issues were a big concern. So what's really changed now? Obviously, a lot of these designs that we're seeing today are stacking SRAM on the top of the logic because you're pulling it out of the die design. And, you know, so what's different about what we're doing now? And what kinds of thermal solutions are you seeing that are being adopted?
Do you want me to start, Jan?
Yeah, why don't you start?
I can start. Nothing has changed. If anything, things have gotten worse in terms of thermals over the last many years. Nothing has changed. It's really, there is significant product value proposition, and you've probably seen this with some of our announcements on the 3D chiplets over the last couple of months. There is so much value proposition for 3D ICs that is effectively what we are saying is with 3D chiplets, we are giving an architectural generation's worth of performance just by 3D stacking. It's unheard of so far. Till now, those performance benefits had not been realized. So that's really what has changed. Now we've been able to realize these performance benefits. And the thermal solutions, just like the tool issues that you talked about, those are barriers that we will eventually overcome as a ecosystem.
Yeah, I'd like to add to that. I agree with Raja. It has gotten worse. The situation has gotten worse. The main challenge with putting logic under DRAM is that the maximum junction temperatures, there's approximately 15-degree delta between max junction temperature for logic and DRAM. So the issue is more of a global across the chip. Just the heat path for the logic was through the DRAM, and the DRAM didn't really contribute significantly to the thermal load. But when you put active piece of silicon on top of active piece of silicon, and it's then in order to validate or verify that the design works, you have to run all kinds of duty cycles and take into account hot spots at each and different duty cycles and what's on and what's off. So it has gotten considerably more complex with 3D structures with active devices in each of the layers.
If I may add, logic on logic or high performance on top of another high performance chip has always been a struggle. We have to manage power, we have to manage thermal hotspot misalignment, meaning you cannot let the hotspots align for the same hot heat solution. Otherwise, for a mobile part, for example, as long as it's logic and memory, we have been doing it. Logic and low speed IO, we have been doing it. So it's essentially two high performing parts on top of each other. That problem has not gone away.
So are there some
Yes,
tools
so
Sorry,
that we
guys.
use-
Hi, Jen. Can I interject for a comment?
Yeah, go ahead. Yes, please.
Yeah, I was thinking that I absolutely agree that hotspots are getting hotter. I would think it probably also creates a hot opportunity, right? And that makes it even more important to perform chip level and system level analysis early on, and potentially have abilities to move the hotspots vertically so they don't overlap, right? By either means of design or workload manipulations, right? I think it's definitely getting hotter, but we love problems. There are more problems to solve. In fact, there are more corners to optimize the problem within.
Do any of you see some new thermal solutions that are being adopted that are different from the things we've been doing in the past?
no, absolutely right. I think the thermals are going to be one of the key focus areas for 3D ICs moving forward. It's always been a key focus area, but it's just going to come into view in a more stark manner, especially with significantly high power density devices when you go to, let's say, N3, N2, and beyond. I think the key is how do we architect this for the right thermals, design for thermals effectively. And for planning optimizations is, of course, a big knob here.
Okay. And do we also see, do you see any new material sets being used? Or are we going to be using the same
In
ones?
some cases, yes, we have experimented and presented, not in the mainstream parts, but yeah, we have thermal, what is that? Exchange, I forget the material, what is it called? But we have shown that some materials can actually be better thermal, have better thermal removal, and you can have a layer of those on top of the processors. We have presented microfluidic cooling. We have presented plates, like big microfluidic plates under your processor. So yeah, I mean, Intel has experimented with many of these things. But in the mainstream products that we sell, we still are not there yet. I mean, it's still fan and heat sinks and heat spreaders.
Well, you guys had a paper at ECTC that talked about some kind of spray coating stuff. Is
Correct.
that
Yes,
anything
yes.
that is that something you're pursuing, or is that just an idea?
Yeah.
you
So
talked about?
we are pursuing, but it has to come to a whatever, like for a mainstream part, it has to come to a cost point that we can use easily in our products. Correct.
Okay,
Yeah,
interesting.
I'm not sure if there's any silver bullets out there. I think certainly design and verification and software control are going to be like Ming said. There's a lot of problems, but there's a lot of levers. But those levers are going to take some pretty sophisticated software, both from a design point of view and as well as from an operation point of view. But I think also it's just going to have to be a lot more attention to detail, and ultimately we're going to have to reduce or improve the efficiency of circuits if they do get compressed, continue to get compressed together. The efficiency of the circuits just has to improve. I mean, we just can't go on increasing the thermal density forever.
I think we kind of heard a little bit about that. So let's shift gears a little bit and talk a little bit about test and inspection issues. Are you all seeing that 3D is more difficult to test than 2D?
Hey, Jan, I had a thermal question
Oh, sure, Larry.
that I put in chat, so you should open the chat.
Oh, I
which
can't
is-
see the chat.
So my question is, Bob Patty mentioned during Paul's talk that the memory that his company developed operated at a higher max operating temperature, and I was wondering if there are any prospects for raising the max operating temperature of the memory.
Good question.
I can probably take that. I think that the question is, is there a memory that exists where if I raise the operating temperature, performance will not degrade? I mean, that's a simple answer to that question. If there is a memory that exists, I'd love to know about it.
Yeah. DRAM has the maximum operating temperature has increased supplier by supplier. So you'd have to go to the Micron, Samsung's, SK's, and look at their spec sheets. But there are different operating temperatures. Nothing that really gets it up to the same level as logic, and even if it did, it doesn't solve the thermal density issue. It just means that a DRAM chip has the same thermal capabilities as a logic chip, which it doesn't today. And there is also an issue with DRAM because it has to be refreshed. And when you get closer to the maximum junction temperature, the refresh rate goes up, and therefore you have to refresh faster, which heats the circuit, and then you end up with thermal runaways. So there's probably no elegant solution here.
Yep.
Any other questions from the audience, from the chats? Bob Patty says that you need to refresh as low as 8 milliseconds and remove more tail bits in the yield. Any other questions from the audience? I'll be monitoring the chat box a little bit better now. So let's talk a little bit about those test and inspection issues. And, are we needing new techniques? Do we need inline process? I mean, what's, Tom, you're certainly currently working with a company that offers some solutions.
Sure. So inline inspection for packages is always an interesting topic because historically packages were designed to not require inline inspection. I mean, if we look at the interconnect pitches, they didn't really scale a whole lot over the past 30 or 40 years. And that was intentionally done because silicon scaling works so well. And if we avoided getting into lithography or getting into structure sizes that require process controls, then we could pretty much blind build. But I think a key question, and I think it's not answered yet, but a key question is, as interconnect scale, whether they're solder based or whether they're direct copper bonds, is some type of inline process control needed? And I think the industry is, to me, it feels like undecided whether it is or not. And also it's kind of undecided as at what point does process control is needed, and what type of data does the industry want to extract from the manufacturing processes, and what type of sensing systems would be acceptable to be used. I think all of those questions are still to be answered.
Yeah, so just to resonate on that point, I remember when the days I started my first job as a DFT engineer, it's actually very elegant, right? You can compartmentalize certain things for structure testing, and then you have a bigger thing that's functional tested. So you can balance the coverage and the cost, right? I think all of that is going to get a little bit more complicated with heterogeneous integration, not only because there are going to be more blocks or chiplets, but there will also be more interactions among them that create cross-chiplet or cross-die interferences in terms of speed path or marginality. I think the way that I see it is that sort of the trade-off between known good die or interconnect or substrate test versus system level test would probably remain a challenge, right? It's a sliding bar. And I think the other thing that's going to be a sliding bar is how much of this test or diagnosis do we do at time 0 out of the factory for outgoing quality versus how much do you take as a fact of life and do a life cycle management afterwards? That I think, again, it was not a new problem, but it'll potentially be a more important problem for 3D IC going forward compared to a simple monolithic chip.
Okay, and let me talk about silicon side. There used to be sort, which is wafer level sort, low speed, various temperatures. Then do die simulation, put it on the package, do a class testing, which is now you are doing a system level testing at some voltage and frequency analysis to bin the parts. Now the problem is we have to do singulated die testing to bin the die, and which is not easy. I mean, as in with probes, you have to singulate the die according to its VF characteristics and combine all the similar looking parts together to get all parts in harmony in some frequency. And that singulated die testing at speed with frequency voltage characterization has become a new test challenge in this entire flow.
Yes, yeah.
But you don't feel like that's an insurmountable challenge, right?
No, because it is. because at the wafer level, you really don't have that many probes to test everything. So you have to figure out with a limited set of wherever you can land. And yeah, there's another challenge here. Your micro bumps are smaller than your test tips, the probe tips. So now you have to figure out how to singulate the die, land your tips that are bigger than your micro bumps, and do frequency characterization. In that, there is not enough power in this particular scenario. I mean, obviously we have figured it out, but that has become a new step, new challenge in our entire product flow.
But what if there are no micro bumps? What if they're just pads? Are you going to probe those pads?
Then you have to do bump processing afterwards. You have to finally attach the die, right? Oh,
Well,
if your test pads are
it.
separated from the bumps, yeah, then you're right. Then you're right. If your test pads are completely separated and like the die area is reserved for test purposes, yeah, you're right in that case.
But of course,
I
that
think
makes the die larger.
Right. I think it's a fundamental geometry limit, right, for the functional connectors, whether it's pads or bumps, unless you have sacrificial bumps or pads. That's just for testing only, right? Tene, that's what you're saying.
Yes. Yeah, exactly.
Yeah.
So are we going to have sacrificial pads? I mean, that's just going to
no. So I don't think we have, but in some cases we have seen it in NVIDIA parts. They have bigger pads between the bumps, and they use them for testing. But I do not want to speak for NVIDIA. If there is anybody from NVIDIA here, they can comment. That's a big challenge. The binning. Yeah. Okay. The question was, what about hybrid bonding? You cannot have sacrificial pads in hybrid bonding scenario. Does anyone want to answer? So I was going to answer that. Yeah, it is going to be a challenge. Go ahead, Bob. Okay, so Bob is saying they are allowing people to put sacrificial pads for testing purposes. Okay, and they don't use copper for the metal generally when you do that.
Okay.
But then doesn't that mean that the chip itself has to have a test engine built into it that can test all of that functionality, because you've only got a limited number of pads, probably not nearly enough to mux everything in, so you'll have to have self-test. Would everyone agree with that?
Yes, Bob is agreeing. Yes.
Yeah.
Okay.
I think there should be a flowing microphone for audience.
Well,
Yeah, we're
I
not
think just to that point, there's got to be a balance for scan-based, right, test access versus BIST. Right? It's not going to be one or nothing. It's going to be both of them for most cases, right?
Yeah.
And once you
And-
put the dice together, there's also a mechanism to daisy chain the scan cells to provide test access for either low speed testing or at speed, high speed 5-to-5 testing. Of course, that doesn't cover the problems internally in the logic, but at least it covers portion of the interconnects. Now, of course, if a bad die, you would be losing it at that point post assembly, right? There's an interesting question on the I think on the chat window, Jen. Just want to
Yeah, so Larry has a question here. When sourcing chiplets from different suppliers, how big a problem is assigning responsibility for yield loss?
I actually asked this question in the morning. I don't have an answer. I mean, it is a difficult problem. That's all I can say.
Yeah. So
I think it's a very, I would concur with. I would
Phil wants
concur
to
with
say something.
Okay,
Just
go
hold
ahead.
on. Just hold on. Phil wants to say something.
That's a good question we just got. I'm suggesting we ask it in a different way and say, does anybody know of any chiplet that anybody has tried to build at two different sources to see what the differences are going to be and what the issues are? Same chiplet, two different sources.
okay, repeat that. We can't hear you.
Okay, same chiplet, two different sources. Does anybody have a chiplet that has been built by two different sources, the same chiplet, not two different chiplets going into the same module? Because that's really one of our issues, right? Are they the same? Are there issues when you assemble them? And we're really not going to know what the real issues are until we try to do that. I'm just saying we're still in the infancy, and I don't think there are a whole lot of examples of that.
I think you're probably right. That they will not be identical, even if they have identical specs.
I think Bob put a comment in the chat box that said, known not bad die. So a KNBD and BIS and BISR are required. So, you know, it sounds to me like we're going to be dealing with a lot of, still have a lot of challenges. So, and kind of going back to that and worrying about who's responsible for what failure. Is the failure analysis going to be a lot more difficult when we're doing a 3D instead of a 2D?
Yeah, I think it would be hugely different. Now, in simpler 3D packages, I think the question on yield responsibility is what's in the gray area. When you have, like, if we go back and think about the last 5 or 10 years of 3D packages, you could bucketize certain functions and say, okay, if this happens, then it's because of that die. If this happens, it's because of that die. And if this happens, it's because of assembly. But there's always gray areas where you have to do failure analysis to figure out what's going on. And maybe you'll never get to root cause. But I think as these packages become more and more complex and functions aren't quite as clearly defined by chips, they might be shared between chips. it's going to be very difficult to do triage on failures to be able to say, okay, it's this chip or that chip. So the gray area between the parts of the design are growing larger, and it's extremely difficult and time consuming and expensive to do failure analysis.
And Larry just made another good comment here about it's not just an issue of how well you're tested, but also of the physical interface. So that's.
I think just to resonate on what Larry said, I think it's a double-edged sword, right? If you look at chiplets or dies sitting on a silicon interposer compared to CSP packages or VGA packages sitting on the board, there's a lot of similarity. On one side of the sword, that complexity for chip on wafer makes it more likely to fail, right? It makes it also harder to pinpoint, i.e. root cause or failure analysis. On the other hand, we could almost argue that because, right, for example, in the case of silicon interposer, the lines basically are higher quality. There's also more opportunities to insert test circuits, right, between the interconnects, because you're writing the lines on silicon. You could almost argue it's easier to point fingers, because to me, responsibility of yield loss, my naive view is it all depends how much confidence you have to point fingers. You can confidently say point fingers to that one chip or that one layer. I think that guy will be responsible, right? But if you're not sure, it'll be hard. I think it's going to the competition of, just to recap, competition between two forces. One is the increased complexity of 3D IC, which makes the finger pointing difficult. The other aspect would be it's now easier to have interconnect or system level test because of the higher density of integration on silicon. So potentially we can do a better job for system level diagnosis in RCA. So which side wins? I'm not quite sure. I don't know.
So I guess we've still got a lot of areas to work on.
Well, engineers love problems. I think this is a good thing to have.
Yeah. So, you know, this, if does anyone think that because of the difficulty in saying, you know, where the problems are and things like that, does it make this a bigger play for the foundries than the OSATs? To do the 3D.
I would say OSATs, yes. OSATs play a big role here. Foundries, not so sure. Foundries will continue to do what they were doing. But OSATs have a bigger responsibility now to do the right assembly process and yield. I mean, maximize their yield.
Jan, is the question that you're asking related to like single provider as opposed to
like a turnkey solution? If you have
yeah.
a turnkey solution, you just, you know, and the foundry is providing you everything, including the package and final test, then is that easier to deal with this complex package structure that we have with the 3D IC?
I think in theory it does, but there might not be, well, there's not a lot of foundries at the high end anyway, but it does severely limit choices, right? Because there's no one company that can do everything. So I think there's also some you know, some business aspects that need to be thought out, that you know, that if you source everything from one company, then you really don't have any choices. So you know, there's a downside to that at all, but certainly everything under one roof would be easier to control in theory.
So Bob Petty has a comment here. He says the benefits of 3D must outweigh the problem risk. And today there are applications where that's true, but that's of course not every application. And then he has a question, will OSATs get to true 3D like hybrid bonding? And I've been asking that question myself. So what does the panel think? Do you see OSATs doing this?
I don't know. I hard to comment, but I think hybrid bonding is going to be more in the fab than OSAT world. So it will be more on the silicon suppliers,
Mhm.
my opinion, because of the density of the connections.
I think I agree with Tanay. I think at least initially, when we talk about a chiplet that is basically a couple of IP blocks that were pulled out from a monolithic design because they needed to be fabbed in a different node, and it just makes a whole lot of sense to use the one foundry for that. But long term, I don't know that it has to stay that way, but I think certainly initially it would be much easier to control, much lower risk to keep the chiplet and the mother chip under one roof.
So is Intel planning on doing something where you fab something at one node at a foundry and then fab something internally at Intel and then put that together in a package?
We are doing it with HBM today. I mean, we are announcing that with HBM. So that is a combination of Intel and external foundry.
Could you elaborate on that a little bit more?
I mean, it has been already published. Like we have HBM stacks inside the same package as our Sapphire Rapids, which is built in Intel.
Right.
So we depend on HBM supply, and then Intel integrates all of that as a solution, end solution.
That's true. Okay, I've got a couple of questions here. One is I think it's a comment, yeah, and a question. Okay, from Randy. I started doing this when one transistor could buy 100 bushels of rice. Now 1 grain of rice will buy 50 to 100 transistors. If this was easy, we wouldn't be here. So the opportunities will always be there for realization. So what are all the perceived biggest 3D ROIs? 3D IC ROIs.
I
Anybody
can
wanna
take that.
touch that one?
Yeah, I can take that, Jan. I think it's pretty straightforward, right? I think someone mentioned earlier as a question, maybe the benefits should outweigh the risks. And I think we are at a point where 3D IC benefits are quite significant that I think the ecosystem is willing to take the additional risk in delivering these solutions. When you have architectures like what we announced with the 3D cache that provide almost a generational worth of performance, like it's better than even an architectural transition in some cases. And it really tells you that those are the points where you take the additional risk and try to solve the potentially unsolvable problems.
Bob Patty had a question here also. He says, when TSMC is assembling Intel Bob wants to know if TSMC is assembling Intel Foundry or vice versa.
I mean,
You guys want to touch that one?
yeah. No, assembly will always be Intel. Yeah.
So maybe let me add just, oh, go ahead.
Oh, I was going to say, if I may, I'd like to comment on Randy's question about, that's a pretty new manifestation of Moore's law. I love the rice analogy, although it's a little bit depressing, but so I wanted to say that the one thing that I'm really excited about 3D IC more than performance, power, is really now the chip designers have a bigger toolbox with more things in it, right? You can build more variety of systems because now you can mix and match chiplets with different functionality on different substrates with different traffic speed of lanes. That to me is more exciting than picojoules or picosecond, right? That to me is really exciting because we can build better, greater things faster, and we just have more tools, right? That I think that's probably, in my view, the biggest ROI for 3D.
Okay. Jan, I had a follow-on
Yeah.
to the
Uh-huh.
TSMC. So I just want to clarify that, and I think, Jan, you've spent a lot of time on this. What is the definition of a chiplet? And there's a couple of different ones, but what I want to focus on is direct copper bonding, and whether you want to call it chiplets or whether it's something, it could be DRAM, so it could be homogeneous, but I think direct copper interconnects puts the product in a different class, and I thought this was what one of the earlier comments was going to head towards, was I think it was Bob's comment about TSMC, that that direct copper, because it really is more like, even though there is nothing in most wafer fabs where we put two wafers together and bond them, or even chips to wafers. I think direct copper bond acts more like a front end process than a back end process, even if it's chips to wafers. So I think that puts it into a different category, and I'm not sure how long it's going to take before that type of process moves into the OSATs, because it would take a lot of investment, a lot of know-how to do that. So I think vertical integration probably will remain predominant in that area for a while.
Mhm. And I think that Randy had another question or comment. He wanted to know anybody's thoughts or comments on ODSA versus CHIPS Alliance. Anybody want to comment on that, or are we just going to let those play out?
Well, this is a little bit outside of my area, but they're kind of different, because ODSA is their goal. And I hope I don't misstate it, but their goal is to commercialize a methodology, including architecture and materials and things like that, for doing solder-based chiplets. I believe at this time they're not really focused on direct copper. Whereas the CHIPS Alliance is, I don't know how to define their objective, but it is copper, and it is more of a disintegrated function, whereas ODSA is maybe a chiplet and a mother chip, but the CHIPS Alliance is massive disintegration. Correct me if I'm wrong, but I think they're significantly different.
Do you mean disintegration or do you mean disaggregation?
Disaggregation.
Yeah. Just want to make sure.
Yeah. Okay. Okay, that's an interesting one. So we also wanted to talk a little bit more about when were we going to see HBM3? I mean, that is definitely a 3D kind of stack. It'll be basically the third installment of this. And when is that going to be used in new applications, and where? And is there at any point where we're going to be able to use this in something other than just the very high performance applications? Anybody want to touch that one? Would that be giving away your product plans?
No, actually, I don't know. I mean, I'm not aware, so I cannot comment.
Okay. Well, we know it's coming.
Yeah, I
It'll
think
be
one
here.
of the well, there's a couple of interesting questions with HBM3. One is that when HBM came out, in particular HBM2, the 8 high, which is actually a 9 high stack, but the 8 high was not that popular because not many not many products were designed around having that much high-speed DRAM available to them, so they just didn't need it. So the 4-high was most popular. But as people learned how to use it, then the ratio of 4-high to 8-high has changed significantly, and now there's applications that want 12-high. Of course, at least one of the HBM manufacturers has announced commercially a 12-high version. But the HBM stack is limited to about 720 microns. So if you add more chips, you can't make the stack taller. You have to make them thinner. And so a key decision for HBM3 is going to be whether it will use copper interconnect, which will give a lot of stack back to silicon and take it out of solder. But that comes with its own set of issues. And I believe the HBM3 spec is still undefined as far as height for the 12-high version.
Yeah, I thought it was defined, but I'm not sure yet. Or I guess it's not defined as a spec. I think SK Hynix put something out there. So let's talk a little bit more about hybrid bonding. I mean, it certainly seems to be being adopted for the 3D stacked chiplets with AMD's V-Cache. What do we see as some of the remaining challenges for the adoption in other applications? I think we kind of touched on this earlier in our discussions, and we certainly touched on whether this is going to be limited to the foundries. And I think the consensus is, at least for a while, it's going to be limited to the foundries. But what do you see as the other challenges?
And Jen, if I may interject, I was waiting for chip makers to comment on your previous question. Can I comment on the previous question, HBM3?
Yeah, go ahead.
Just in general terms, nothing product specific, no schedules, right? Very specifically, or very generally speaking, I just wanted to say that certainly high performance compute, AI, right, deep learning have been a classical applications for HBM and certainly HBM3. And newer applications that we've seen in the news, autonomous driving that requires a lot of compute and training, would also be a potential area of interest. Again, just general terms for that second bullet there in terms of cost, it is definitely more expensive compared to simpler memory connections, off-chip memory collections. And there's a reason for it, right? There's better power efficiency, higher bandwidth. And I think the one thing that I kind of learned myself is that as you look deeper, that whatever you think you're getting, you're paying more on the HBM, that interconnect, you're actually getting it back from the host SoC, because the connection is such that the bandwidth per millimeter of beachfront is actually a lot more efficient for HBM type of connections. So whatever dollar value you think you have lost on that interconnect, you're gaining it back on the increased efficiency on your high-end SoC, which is on a bleeding edge process node. Again, in general terms, I just want to point out that out, right? It's not just optimizing an interconnect or a memory, and it's certainly not just optimizing the SoC, but it's all of these together, right, in a single package. That, I think, it's again goes back to my comments earlier. The 3D IC really, to me, makes chip design a lot more interesting, right? Now there are a lot more things to play with, right? This is another example of that. So, hope that is helpful, Jen.
Yes, thank you. So does anybody else want to comment on some of the issues for hybrid bonding for the 3D stacking of chiplets? Or
I can take a shot at it, Jan. I think as we introduced the V-Cache, obviously there's a lot of challenges that you have to overcome. Of course, power delivery, thermals, design for test, design for yield, design for reliability. All of those things are just getting started as an ecosystem, right? once we start running more and more production and more volume, there's a lot more issues that need to get ironed out. And I think the partners, our ecosystem partners will adapt, whether it's design tools or new methodologies for design for test. What are the red binning strategies? Are we going to do chip on wafer or wafer on wafer? Everything we're still at an infancy. We just given birth to the baby, and it has to grow up to an adult and mature. So I think it's early to say that we have solved all the challenges. In fact, we have not. We are just getting started and defining what even the challenges are going to look like in 5-10 years from now. This to me is almost like starting off on, let's say, FinFETs or gate-all-arounds or anything like that. That's the level of changes we're going to see in the ecosystem to enable these technologies moving forward.
Anybody else care to make a comment? I mean, I think it's certainly I'd agree with everybody. It's a very exciting time. I mean, it's certainly not a dull moment here.
It's the most fun I've had ever in the industry. So I'd like to make a comment about hybrid bonding. You put the question about wafer on wafer and chip on wafer at the end, but actually I think that is a key issue. And wafer on wafer has been in production, Sony, for example, for some time in high volumes. So and there's a fairly good infrastructure out there for doing wafer on wafer. Now there's some issues as pad sizes and pitches get small, and there's some reticles. Reticle alignment becomes an issue and things like that. But in general, I think we can say that wafer on wafer is fairly mature. However, when we move to chip on wafer, even though it's the same fundamental process, a lot of things change, and it not quite so mature. There's issues with, like, for example, debris from singulation that doesn't affect wafer on wafer at all, but is a big challenge for the chip on wafer industry. And and there's other issues. For example, the efficiency of placement is a significant difference. I mean, one of the reasons that HBM is expensive is because each of those dies is stacked one by one. They may be gang bonded when it comes to reflow, but their placement has to be very accurate, and it's done one by one. So chip on wafer would be the same thing. So, but as we've seen, as industry heads towards 3 nanometer, Jan, I think you raised the question earlier. Will there be any monolithic 3 nanometer chips designed? I don't know the answer to that. Maybe some of our other panelists can comment, but I think there's going to be a whole lot that will be done with chiplets, and we've got a relatively short amount of time to resolve a lot of questions.
Interesting. So we have another comment related to something that we just discussed a little bit earlier. Paul says that that they recently ran an ML application on an HBM Xilinx part and a DDR Xilinx part, and the HBM version had an almost 2x better TOPS per dollar. So I think that goes back to what you were saying, Ming.
Yep, exactly. Yeah, system level, like performance,
Verify.
power, cost. Yep.
So interestingly, Tom, on the comments you were making on the infrastructure, I mean, I think if you look at the number of tools shipped for wafer on wafer compared to die on wafer, the number is huge because of the CMOS image sensors that are wafer on wafer part of that. And plus we know that companies like YMTC are doing their flash fabrication process with doing some wafer on wafer stacking, and others are for flash is a different a little bit different animal. But so I mean, I think people don't realize how much infrastructure is there for wafer on wafer. So we actually were trying to tally up the number of systems that were shipped, and it was just phenomenal, the difference. So, but I mean, granted, an image sensor is a whole lot different from stacking logic and some of these other things. But does anybody feel like that we're lacking in the tools, or do you think that the tools are coming along pretty well for this, for the die to wafer stacking?
Are you talking about tools in the assembly flow?
Yeah, for die to wafer versus wafer on wafer, because we know there's a lot of tools out there for wafer on wafer from the image sensor business, but do you feel like you're seeing what you need from the tool vendors for the die, for the chip on wafer or die on wafer?
Well, I think some of the, for example, on the assembly side, some of those tools are just starting to be shipped. So so I think the answer is still coming. And I'm not sure that the tool manufacturers have hit the kind of throughput that that the semiconductor manufacturers would like to see, but there's definitely tools that are, that were designed just around direct copper chip on wafer type assembly that are, that are starting to ship. There's still I think some gaps in the industry. For example, let's say that we just came in, it's Monday morning, we just turned on the bonder and we built the first part. How do we know that that part was good? We can use a scanning acoustic microscope and we can see if there's a big particle under it. But how do we know that the two pads have really diffused into each other enough that there's no major voids or oxidation or other contamination between them that impeded the bonding? Right now, I think really the only option you have is send it to the lab, cross-section it, and fib or tem it, which is kind of slow. So I think there's still some gaps in the process flows here before we can say it's a commercial process.
Hey Jan, there is a question in the room. Just a minute.
Oh, okay, great.
There are manufacturers building high accuracy pick and place tools now, or they're working on that for die to wafer bonding, and they're leaving out the heating. So they're building them for direct bonding and copper to copper bonding. So it is taking place. So there's definitely a call for it. These are sub-micron accuracy tools, high speed.
Sir, I'll repeat. So you're saying there are sub-micron accuracy tools for pick and place. You want to come here and say? Sorry about that.
This is Gil Fountain from Xperi. So we do know that there are pick and place vendors working on high accuracy die to wafer pick and place tools that are submicron, and they're leaving out the heating options for the tool. So we know that they're building these for direct bonding and copper to copper bonding.
So more good stuff to come. Okay, so I think we're almost at the end of our time. Does anybody else have a question or comment that you want to make? Because I think we've had a very interesting discussion and we certainly covered a lot of ground here. I don't think anybody's going to be bored in the next year.